Hey, Physics 30. So today we're going to be talking about how to calculate the speed of an EMR, or speed of light, in this case. So hopefully by now, if you've already watched the... Actually, I want you, don't watch this right now. Go watch the other two videos, or three, or I don't know how many videos I'm going to link for this, on how previous scientists calculated the speed of light. The TED Talk with Adam Savage, I believe it is really good. It talks about Fizeau and how he used that cogged wheel device to determine the speed of light. I believe I'm going to put one about Galileo and how he used the stars and the planets to do that. Go watch those. Great. Come back. So we are going to calculate the speed of light. You're going to have to know some different versions of how to calculate it, but the one main version is Alberta Michelson here. He used a very similar experiment to Fizeau. Instead of using a cogged tooth wheel, right? He used a rotating mirror system. And when we talk about this rotating mirror system, you're gonna think of some of these frequencies that the rotating mirror is going at. Like if you look at this picture right here, this is the top-down picture. We'll talk about that picture in a second. But this frequency, it's huge. It's 553 hertz, which means it's this rotating mirror. It's a pretty big picture. I'll grab a picture and I'll pull it in a bit here. But this device, I'll just do it right now, actually. Okay, so I found a few of some pictures of Michelson. It's actually Albert A. Michelson. Sorry, not Alberta Michelson, but Albert A. Michelson's experiment. Here's one from a Naval Academy here. You can see there it is, Albert A. Michelson's portrait, or it's not really a portrait in there, somewhere there's a portrait. Down here it says revolving mirrors. So this up here is a mirror. So in the top part there's a mirror and it would spin, but it's a single, or it's a double-sided mirror, or you could say almost a single-sided mirror depending on how he wants to do it. And you would get that spinning pretty fast. This is, you'll see it in the video. I'll either link the video or we're actually going to watch it together and I'll talk about the video as it goes. This is a very inefficient method. You'd have to spin really fast for things to work because they have to spin completely around once before the light comes back, and you'll see what that means in a second. One of his other experiments here, this is one, it's a mile-long tube that he created. It's pretty much almost vacuum. Inside the mile-long tube, the reason it's so long is that it has the light bouncing back and forth a few times to increase the distance the light has to travel. And then it's going to strike this rotating mirror. And what the experiment is all about, and I'll show you a little video here. We're going to actually maybe just watch the video together. Put it in cinematic mode here. Hopefully the sound won't drown out my voice. So we'll pause it. Here's that cog tooth as well that you saw.
In the Foucault method, the wheel was replaced by a rotating mirror. Only during the short time interval while the mirror is in this position can the light from the source reach the lens. A moment before and a moment later, the light misses the lens. If the mirror remains stationary at this position, the light proceeds through the lens and thence to a very distant lens-mirror combination, from which it is reflected back to the rotating mirror. There, the reflected light forms an image, I. However, if the mirror has rotated to this position, while the light goes to the distant mirror and back, an image I prime is formed at a position displaced from I. Thus, the rotating mirror breaks up the light into wave trains, which on their return form a new image, I prime. The displacement I prime, along with the rotational speed of the revolving mirror and the distance between the mirrors, provides the means for calculating the speed of light.
Okay, so that gets a little bit confusing. We don't do it that way anymore. This is the way.
Improved upon Foucault's method.
So in Michelson's experiment here, we got the rotating mirror on this side over here. Right there, there's a rotating mirror. It's going to start spinning around. And I like, rather than the static image that's on the the notes there. I like this because it's going to be rotating soon. You're going to see what happens. Don't be fooled. It's not shooting out individual little beams of photons. Continuous beam coming out. They're only just showing the beams of light that actually make it over to that mirror on the other side. So the light's going to go from over there to this side over here, and you're only going to see those beams. Okay, so I'll show you what it looks like here.
By using a revolving many-sided mirror. And instead of measuring the displacement of the final image, Michelson varied the speed of the mirror until there was no displacement. We shall consider the behavior of an 8-sided mirror. Light from a source is reflected to a distant mirror. The returning light is reflected by the 8-sided mirror to a measuring point in a telescope. When the mirror is set in rotation, the light will arrive at the measuring point only if the mirror makes exactly 1/8 of a revolution in the time it takes the light to go to the distant mirror and back.
Okay, so that 1/8 of a rotation is very important for some of the math we're going to do. You can watch that mirror as it spins around, right? So it doesn't have the mirror that. Sorry, if I skip ahead just a little bit here. Okay, so the mirror at the top. So this mirror where the beam hits the light, that mirror doesn't have to go all the way down to the bottom. It just has to rotate just slightly so the mirror that's right here can get down to that spot. So you just watch that move very slowly there. I'll get in the way here.
If the mirror does not make exactly 1/8 of a revolution in the time it takes the light to go to the distant mirror and back, the light will not arrive at the measuring point.
Not enough. It's kind of weird that they keep on going over and over again. Okay, so that is going to be important when we do our math. So here's our rotating mirror. Okay, we put Fizeau in here because it's a very similar process as the cog-tooth wheel. The light has to get back in the right amount of time to get through either between the two teeth in the cog-tooth wheel or to the mirror at the right angle to bounce properly. So this is the rotating mirror. The rotating mirror, I don't know, it's about that big or so, right? Spins really, really fast. It does have a habit of breaking apart. We're gonna deal with 8-sided. We could do any size mirrors, one side or 2-sided, 1-sided, all the way up to 100-sided mirrors. The experiments I think he did were like 16-sided mirror or so. But the math we're going to do here is regarding this 8-sided mirror. Now these two distances here, this distance and this distance are relatively small compared to the distance down here, the very bottom. So this is going to shoot off somewhere. It's going to go hit that mirror. And it's going to be, according to the question down, you can see down here. My thing's not working anymore. Okay, there you go. You can see from the question down here, it's about 35 kilometers away. So it's going to travel 35 kilometers this way, then hit the mirror and then travel 35 kilometers back. So that's going to be important for our math as well. Okay, so Michelson's mirror. So Michelson's mirror, if you see from the picture, is going to rotate at a very specific speed. You can see it's rotating at a frequency of 533. I think it changed from one page to another. So it's 553 up here. It doesn't really matter. We'll use the 533 and see if that's any different. So it's rotating at this frequency, the 533. It's going to, the beam of light's going to come down. It's going to hit the mirror. This is my 8-sided mirror. I'm going to just redraw here. Well, it's a horrible 8-sided mirror. It's going to hit the mirror. It's going to bounce off, travel 35 kilometers, hit this other mirror system here. I think you saw that it bounced around a few times here. It'll do a bunch more bouncing this from the mile-long tube. Obviously, it wasn't 35 kilometers away. We could bounce lots within that tube, back and forth a bunch of times. Get that distance. It's going to come back, and it's going to hit this mirror. It's not going to hit this mirror as is. It's going to hit this mirror. That's going to rotate 1/8 This is 1/8 of a rotation over to the new spot, because this is always rotating, right? So that mirror that was right here after this got hit up here, this mirror is going to rotate 1/8 of its position. It's going to get in the right spot just in time, and then it's going to come down, and then Albert Friseau can see the beam of light down here in his measurement system that he has. Okay, so the 1/8 is very important. So what we know about light travels at a constant speed, right? And he knew that too. So we can use this formula, and he knew to use this formula. D is equal to V over T. Based on the experiment, we know that this is traveling 70 kilometers, or 70,000 meters, right? If you want, I'm going to write this down later on, but the distance this has to travel is 2 times that distance. So this formula actually turns into 2 times the distance to the mirror over T. Okay, you can put in the 70,000 for. I'm going to create a general formula here first. This formula is not going to be on your formula sheet, so it's one of those you either have to remember or write on your formula sheet. That's fine by me if you just write it on your formula sheet. Okay, the next part is trying to figure, okay, we have this frequency. We know it only has to go 1/8 of a rotation. How do I use those two things to find the period of this, not the period, the time that takes the light to go back and forth? The time is only 1/8, but is 1/8 of a full rotation, right? So if it starts up here and it's going to go around, that's a full rotation around. And the time of a full rotation is T, the period, right? Okay. So I really only have to go, because it doesn't have to go a full rotation, it only has to go 1/8 of that. The time is 1/8 of the full period. Okay. So I can put that in there, but 1/8, the reason we have 1/8 is that this is the number of mirrors, right? It could be going faster, like the mirror, this adjacent mirror doesn't have to get there. The mirror that it hit could actually get all the way down there in time if it was going faster, or the mirror that was on the top could get there in time if it was going faster. This is just the minimum speed. You can go faster, but anything less than this is not going to work. The minimum 1/8 of this one, okay? So I'm just going to replace the 8 with n for the number of mirrors, right? So it's 1 over n times t. So what I'm going to do I'm going to just put that into this formula here. So I'm going to say V is equal to 2 times d over 1 over n times t. And this is going to simplify because that's a fraction. You divide by a fraction. We take the reciprocal. 2 times d times n over t. Okay, but the question doesn't have t. The question has frequency. So what we know about frequency and period is that they are reciprocals of each other. Frequency is 1 over t. Okay, so that means t is equal to 1 over frequency. So I'm going to put that into this formula as well. And I'm going to get this. 2 times dn over 1 over f. And that, again, is another fraction, so that's going to flip over to the front, to the top there, sorry. You get 2 times d times n times f, or 2 d and f. Now the 2 is only because that's go there and back. They just tell you the there and back distance, and you don't have to worry about the 2. So I'm going to put all my numbers in here and see what we get. You get 2 times the distance, which is 35,000. This is before I times by 2, times the 8, times the frequency. In this question, it says 533. Okay, not just as much, put meters there. Pull out our calculator. We get 70,000 times 8 times 533. This is just the math, some of the math in our head here. And we get 2.98 times 10 to the 8 meters per second. If I use the 553, I get 3.01. I get pretty close to the numbers that we should be getting. So that's how he calculated the speed of light. That's all I really wanted to do with this lesson, this video. It's pretty easy. The next week, though, We're only going to do the 2 lessons this week because of the test. I want to do the extra quiz, the magnetism test today or this week. So that's all I wanted to show you for this. Next week, we're going to be doing reflection, and we're going to do all sorts of diagrams and stuff. I'm going to put a link in the classroom there for an extra PDF file, which is a picture or a couple pictures of these concave and convex mirrors. And there's going to be some other pictures in there of, you can keep on going down here, of diverging and converging mirrors. So if you have access to a printer, you can print those off and follow along when you're drawing the pictures. If you don't have access to a printer, then, I don't know, draw by hand. You're fine, just have to get a ruler. You don't necessarily need a protractor, but you definitely need a ruler to draw some of these pictures. So next week after our magnetism test, we'll continue on with this EMR stuff, and we'll talk about reflection. I'll see you then. Bye.